they are still stationary. And as long as I can partition the whole time series into different segments of stationary time series, and then I can go back to use my stationary time series technique. So say this is a toy example. The red line here, the ground truth, and there's a mean shift in our time series. And I generate something and I calculate the Q sum. So the Q sum is basically to say, okay, I treat each time point as a potential change point, and I calculate the normalized difference in means of the two parts. And I plot it out, and okay, so the one which has the largest, in terms of magnitude of the Q sum, that will be a potential change point. So there are many papers on it, and recently there are some high-dimensional settings talking about the high-dimensional Q sum. I think Richard Samuels and his PhD student in Cambridge also have a very recent one in terms of a high-dimensional change point, in terms of shifting in mean. Of course, in brain imaging, people are also borrowing this kind of change point idea. So there are different papers. But here what we want to say is, what we are interested in is actually we call the network structure change point. Or if we just forget about the network, this is the change point in terms of the covariance in the high dimensional time series. So it's actually very different from the Q sum idea. But the key thing what we are seeking is the same. In Q sum, if you are looking for a change point in terms of mean, you are trying to get some normalize the difference in terms of means, right? And then what will be a good criterion value for the covariance change? So that's one of our novelty, and I'm going to come to that soon. So the key sectors involved in this paper, the first is the change point detection. That's what I've already said, and the second part is community detection networks. I really didn't know how much I should say, but I mean, if you are already kind of sick of community detection in the last few weeks, I apologize. So this is a general idea of community detection, and this is from this very famous data set, and the picture is from one of my paper with two people at Columbia, my two collaborators. So here is a school friendship network. Each node here is a student, and if there's an edge connecting two nodes, that means at least one of these two claimed that the other is his or her friend. So you get this network, and you want to find some communities. By communities, I mean it's a group of nodes which are tightly knit together but loosely connected with others. Okay, so basically I want to do a clustering in terms of nodes. And here actually I can get 3 different communities. They coincide with a year group. So this is the idea of community detection in terms of network. And maybe I can specify one more thing. In this one, and also the things I'm going to talk about later, we are aiming for undirected simple graph, which means the edges here, they have no direction, and there's no self loop, and there are no multiple edges. Okay. Okay, so finally, this is our method. We call it a network change point detection. Network change point detection. So here's the workflow. The idea is like this. We start from a data matrix. This is our high-dimensional time series. Y is a matrix of T by N. And T is the number of points. P is the number of voxels, region of interest, or nodes. Okay? And just like if you are familiar with Q sum, what they are doing is they go through all the possible time points, and they partition the whole time series into 2 parts, and they calculate the mean respectively. So what we do here is the same. We also go through all the possible points, and at each point we divide the whole time series into 2 parts. The one prior to this one and the one after this one. But now here's the difference. Here's the difference. For each part, we calculate the correlation matrix. So we get YL and YR each of like TL by P, TR by P, and we can get the correlation matrices for these two parts. And both correlation matrices are of dimension P by P. And then for using this correlation matrix as a weight as the adjacency matrix of a weighted graph, we can actually do spectral clustering. May I ask how many people here know spectral clustering? Okay, good, thanks. Majority. Okay, so and then we do clustering, spectral clustering. We get the centroids of each cluster. We get the community label of each node. Okay, I still notice there are some people who didn't raise their hands, and the spectral clustering is to say I have a graph, I can construct an adjacency matrix, and then I can use the eigenstructure of this matrix, adjacency matrix to embed this. This is a P by P matrix, right? I can embed this P by P data set into a P by K. K is a pre-specified number. It's the number of communities I'm assuming. So it's a dimension reduction from a P-dimensional data set to a K-dimensional data set. And then using this K-dimensional data set, I do K-means. So now I have a, say, P by K matrix, right? I treat each row as a data point in this K-dimensional space, right? And I do K-means. I just cluster them into K different groups. So dimension reduction and the K-means, that's spectral clustering. Okay, that's a brief version of spectral clustering. And then we get this spectral clustering, we get the centroids of each cluster, we get the community labels of each node. The next thing we are doing is we make something called centralized matrices. It's slightly different from just the centroids of their their own. I'll go to talk about it later. I'm going to talk about it later. Okay, anyway, so now you have a K-dimensional embedding of a P-dimensional data set for each of the time series. And in Q-sum, what we are doing is when we partition, we try to find the normalized mean, and then we take a difference, and that gives you the Q-sum, right? So what will be the different measurement we are using here? We come to the thing which is called, well, this is the singular values. So it's the singular values of UL transpose UR. And the idea behind, I'm going to talk about it later, but this is the analog of principal angles. And the last step is just to use stationary bootstrap to test whether the change point we are finding is significant or not. So partition first, doing spectral clustering, and try to use the singular values as the criterion value for each point. And then we test whether the change points we are finding is significant or not. Okay, some details. So in the spectral clustering, I think this is the question one of our referees asked. Oh, I forgot to thank the editor and the guest editors and the referees. I really need to thank the guest editor because I think it's Veronica, right? Even in the second round, I'm very ashamed to admit that even in the second round, she pointed out 25 typos. So thanks very much. Well, okay, so back to this one-node precision matrices, because the referee was asking, okay, so you are anyway trying to study the correlation between different nodes, different voxels, different region of interest. Why not use precision matrices? We actually find a very good answer to that. I quite like our answer. So the thing is, let's think about precision matrices. This is a high-dimensional data set, right? And we know there are tons of methods, tons of papers to estimate the high-dimensional precision matrices. But the thing is, they all need a sparsity assumption, and this sparsity assumption comes to at least the row sum should be the row should be sparse. And if we go back to the brain networks, that comes to the point that each voxel or each region of interest, although there are like hundreds or thousands of any other voxels, only a few of them are connected to this certain change point. So certain region of interest, right? So that's how we interpret rho sparsity in the brain network. But is that realistic? And what's the sparsity assumption we are having here? What we are having is not that one voxel only have a few other which are correlated to its own. It's actually, although this is a P, there are P nodes in this network, there are only K communities. So the sparsity assumption actually comes down to the number of communities. And if we think this, then still if we think this is Stochastic block model, right? So for each node, still there are P over K nodes which can be associated with this certain node. So this is more realistic in the brain network or in other high-dimensional networks. That's why we are not using precision matrices. And point 2. Adjacency matrix we are using in practice is actually we're just using the correlation matrix here. And the third point I'm going to make is the number of K in terms of K-means and in terms of spectral clustering. Well, we all know there are papers, even I have a paper on in terms of how to choose the number of communities. Well, we call it how many communities are there. But I have to admit, it's under very strong assumptions. And for this one, we don't really want to use very strong assumptions to assume our brains. So first I want to say I don't know how to choose K. But the good thing is, from numerical experiments, what we observe is as long as you overestimate the number of communities, you can get a robust estimate. So that's good news for us. Say if you are given a brain imaging data set and you ask your neuroscientist what's his guess of the number of communities there, and you double it, still it's way fewer than the number of voxels or number of region of interest, but you can get a robust estimate. So that's good news. I said before, there's a centralized matrix U. So the thing is, when you get the spectral clustering, what you will get is the centroids of each community, and you will also know the number, the community label for each node. So usually, what we have is we have like Zi, Ci, and I from 1 to P, this number of nodes. So what we are having for this U here is a CZ1, CZP. We just replace the representation of each node by its centroids to reduce some noise. And this works good, at least in numerical experiments. So this is our centralized matrix. Yep. Okay. And then I said we will have some criterion for each certain time point. And the time point we are using is we call singular values. That's the singular values of UL transpose UL and UL transpose UR. So how did we get this idea? This is actually from the principal angle idea. So principal angles, they say if you want to measure the difference between two unit vectors, what will be the best measurement? That will be the acute angles between these two unit vectors, right? And now if you have two spaces, what will be a good measurement of the difference between these two? Then that's the generalized idea of the acute angles that comes to the principal angles. Principal angles actually can be calculated as V1 and V2 are the basis of space 1 and space 2. Respectively, that will be the singular values of V1 transpose V2, and that's arc cosine of, and then the arc cosine of the singular values are actually the principal angles. So this is the idea of the singular values. The difference between principal angles, and the thing we are using here is actually we didn't normalize it. We're just using an analog of the principal angles. One last thing, I only learned this a few weeks ago when Steve Maron was giving a talk here, and he was using the principal angle analysis in his paper, and he mentioned something which is called the generalized principal angle analysis. So that actually comes from the fact another way to calculate the principal angles between two subspaces is actually if you put these two matrices together, you get a factor matrix like V. And then the 1 plus sigma, shouldn't be sigma, should be arc cosine. Anyway, 1 plus arc cosine sigma I from 1 to d are also the singular values of the matrix, of this matrix. So for only if you are interested in two subspaces, you don't see the point of coming to this one. But if you have more subspaces, you want to calculate their generalized difference. If we have K matrix, let's say, you can just V1 up to Vk here, and you only need to calculate the singular values of this very fat matrix. This is definitely not in this paper. It's just a side note. Sorry. So I guess many of you here maybe know Piotr Fritz-Lewich's wide BS, or by binary segmentation. So we are actually thinking if we can extend our method to using an interval, and if you every time you randomly sample an interval, and then you will partition the whole time series into 3 blocks, and if you want to still get a criterion value for this new partitioned time series, you can actually use this generalized idea, and this will mention again later in my talk. Well, this is just some technical issues in our method. So all the dots here I'm plotting is actually the criterion value, which is the singular values. Well, again, as you can think, because the singular values are the arc cosine, the cosine of the principal angles. So the smaller the singular values is, the larger the distance is. So not different from Q-sum. They are trying to find the largest one. We are trying to find the smallest one. Anyway, so we plot all the criterion values here, but if you can see clearly, there are some red ones. So the idea is we are thinking anyway, the underlying thing should be smooth. If there is something which has very different values from both its left and right neighbor, we think that's an outlier and we delete them. So before we try to find the smallest one, which the one with smallest criterion value, we first delete all the outliers. And here are some simulations. We have 3 different settings, and within each setting, each color represents a certain community. So from this one, for instance, we have 3 change points here, 2 change points here, 1 change point here. And our number of nodes here, 400, 600, 800, and time point 200, 400, 600. And we generate a stochastic block model. So this is the P between, probability between and the probability within. And the correlation matrix we are using 2 type and equal correlation matrices and the top list correlation matrices. Because this is the simulation, so we can actually plot the density of each point being the potential change, being the change point. And the red vertical lines here are the true change point. And you can see using our method, the peak actually coincides. Well, this one missed out a little bit, but I guess in change point detection area, we have the tolerance for a certain width. So basically, our method performs very well, and some more simulation results. We have a true positive, a false positive. Well, this is a modified false positive. The thing is, we notice, we call this is edge phenomenon. We notice that if a certain potential change point is close to the edge, close to time point 0, close to time point t, it tends to be a false positive. And we just delete those which are very close to the edge. And after this deletion, we improved a little bit. And from here, you can see the K0, K node here is the true number of communities we are using, and the k here is the number of communities we are using in our method. So if you overestimate k, it performs good. So okay, it's a little bit hard to explain, but let me just, they're just repetition for, their representations for each simulation setting. But let's focus on the first one. Here, this point is actually the estimated change point we got from our method. And with the upper panel is if we were acted if as we know the true labels, because it's simulation data, we know the true labels, and we can see exactly this is a change point. And here you can see different colors. It's because we are just using the communities we are generating from our method, because we overestimate the number of communities. But I guess you only need to focus on the upper panel because they are the true labels. True labels with estimated change points, well, that tells you exactly that's the change point. We also have some real data analysis, but I think I don't really have too much time. Here is a resting data set. Well, these days people are also interested in what you are thinking when you are told to rest. Well, we don't really know, but we try to find out how many different things you've been thinking when you are told you are rest. Thanks. So here's the resting data set, and I'm just going to, so we have so many subjects, and we find the change point of them. So the good thing of this is no one knows the ground truth. You won't criticize me. We do the same thing, but so we can actually see, we can find some change point, although we are not sure whether they are truth or false. Different subjects, each row is one subject and each state. Okay, this is something interesting. So remember what I said for the criterion value. For the criterion value, like, well, if you are more familiar with the Q-sum, for Q-sum, if you want to find the change point, you want to find the largest Q-sum point, right? Just like in our case, we want to find the smallest singular value point to maximum the difference of the two parts. But here, what we are doing is we want to see how similar two people are. So if you've already done some like change point detection and partition my experiment into like three parts, and you've already done that to yourself, and you want to see if at a certain point I'm thinking something similar as what you are thinking, and then you can still using the principal angle idea or singular values idea, and now in this case you want to find the largest singular value, which means these principal angles are the smallest. Okay, so we can also do multiple subjects comparison. Okay, discussion. Contribution, yes. To be frank, I'm not very familiar with the neuroscience area, but I rely on Ivor, who is the other author here. He says it's a novel thing in the neuroscience, and I believe so. And in terms of network and change point detection, I think I'm very confident to say for the high-dimensional change point detection, if you want to test the difference in terms of the covariance change, I think this is something very new. And also cross-subjects comparison. Do you remember what I just mentioned? I recently learned something from Steve Maron's talk to say there's another way to represent the principal angles, and by using that, they call generalized principal angle analysis. We can actually compare like not just two people. We can compare like three people, even more people, if we are thinking of similar things. So this is a cross-subject comparison, and yeah, as you can think, this is definitely what I'm talking about here. Although I'm motivated by the fMRI data, I'm definitely not restricted to fMRI data. For other type of brain image data, say EEG, MEG, as long as you give me a high-dimensional time series, I can do change point detection in terms of the covariance, in terms of network structure for you. And also this can be used for other area like the financial data set, so on and so forth. Yeah, I think that's all for me. Thanks very much.
Good. Questions?
Thank you very much. It was a very interesting talk. Very nice methodology. I just wonder about the applicability. So with spectral clustering, when you've got sparse or very sparse networks, spectral clustering is not necessarily robust because one node can have large influence. So does your method have any kind of sparsity restrictions, so the network can't be too sparse?
So first, may I ask when you're talking about the sparsity in terms of spectral clustering, are you thinking of a particular theorem or paper, or how sparse it is? I think because, well, as far as I know, even if you want to achieve some good performance of spectral clustering, it can't be too sparse. Am I right to say that? Yeah.
I don't think there are any hard and fast results. I think it's just empirical that people know if you've got a sparse network and a node with high degree, then that can mess up.
Yeah, we highly rely on spectral clustering. So if they can't achieve that, we can't either. Thanks.
Thanks for the nice talk. I wanted to ask, do you have a certain condition or regime on this principal angle between the two subspaces, such that the change point detection sometimes become easier or difficult based on that condition? Is it like a signal to noise ratio maybe?
Okay, so first I have to admit, well, maybe I should list one more thing here. Is another thing we're working on is the theoretical performance of our method. Because this is submission to JSSC, we don't require theorems. but I am interested in theory. Yes, so I don't really know the theoretical limitations and advantage of this one yet. But what do you mean by the principal angle? So
when you split the data and trying to find the principal angle between the two subspaces, depending on the value of the principal angle, if the problem becomes sometimes easier or harder, like some kind of regime.
Oh, okay, I understand now. So I guess, well, I suspect there definitely should be, like if you just do a change point detection in terms of the means, you need to be not too small. And also, if you are testing multiple change points, two consecutive change points, they have to be far away with each other enough. So we definitely need all these kinds of conditions. Yeah, definitely. Thanks.
Question? Yep.
How large can the dimension get before either numerical issues or just time?
Well, yes, I have it here. So we're actually quite proud of ourselves because for this data set, it only is just on the laptop. It's not this laptop, but it's like just 2 minutes. So compared to other, I'm aware of some other neuroimaging tools. Let's say in MATLAB they have GIFT toolbox. We are faster than them, but we are doing slightly different things.
If P increases greatly.
Okay, so that basically comes to the point. You see what we are doing here. We actually have 2 points which might be time consuming. The first is we are going through all the possible time points. We are doing binary segmentation, right? For each time point you need to do one thing. But another thing is we are actually doing the SVD. So I suppose as long as SVD can handle your dimension, then this one can. Then it's just it's a matter of time, right? It's just SVD, and you just try to first do spectral clustering as SVD, and then you try to calculate singular value as SVD. So it's all a matter of SVD's limitation.
Additional questions? Maybe I have one more question that I want to ask. This basically, in some sense, the network that is there is you keep it very latent because the question was asked about sparse networks. Mm-hmm. But in some sense, you just take R as your as a kind of an approximation of your adjacency matrix. It's like a kind of a continuous valued adjacency matrix. So does that make the method much more robust, basically, because you kind of have a complete graph with weights on it that are somewhere between -1 and 1.
So what you are suggesting is maybe we can set some threshold to say as long as it's greater than 0.5, I say this is 1, other than this is 0.
But the other way was basically just to suggest that maybe is it exactly the fact that you use R is that making the method rather robust to, which wouldn't be the case if you had actually the real adjacency matrix.
Yeah, sure. And also what we are observing is just a time series and a high dimensional one. We are creating a network. We don't really, so although I'm plotting here, but that's actually, we are using some threshold just for the visualization purpose, to say either one edge or no edge. Well, it seems you that's a compliment when I say yes, that makes it robust. Thanks.
All right, so if there's no further questions, then let's thank the speaker again.